Hello, engineering materials. Today I'm going to talk about the engineering materials are broadly classified as ferrous materials, non-ferrous materials like aluminium, magnesium, copper, nickel, titanium, plastics, thermoplastics and thermosets, ceramic, diamonds, composite materials, nanomaterials. Engineering materials, what a layman can think, it is based on the cost, but no, it is actually selected based on the mechanical, physical, chemical, and manufacturing properties. The secondary properties are cost, availability, appearance, service life, and recyclability. So, contrary to the common belief, the cost is considered uh, as a last factor, and the mechanical properties are the most important properties, and the ferrous materials are the most important materials because in the developed countries or developing countries the lot of work is being done on the materials which on the designs which involves the ferrous materials, bridges, structures, flyovers, etc. Right now, whenever we talk about any materials, there's a very important concept that's called stress and strain. Stress is simply the internal resisting force per unit area. It's not pressure. Pressure is actually the external force per unit area. It's generally considered for the fluids, but for the solids, the stress is very important because it is the internal resisting force per unit area. It is developed within the material and it is defined as the restoring force upon resisting area. The force has a unit Newton and the area has a unit meter square. Therefore, the unit of stress becomes Newton per meter square or Pascal. It is similar to the pressure, but the concept is entirely different. Types of stresses, that's also we have to know. Normal stresses, shear stresses. Primarily, they are of two types. One is normal and another is shear. The normal, as you can see, the resisting area and the direction of the restoring force, it's actually 90-degree, right? And in the tangential stress, the direction, the orientation of the restoring forces and the resisting area is actually parallel. They are parallel to each other, right? And normal stresses are further classified as tensile stresses, compressive stresses, volumetric stresses, direct stresses, indirect stresses. Similarly, the shear stresses are also classified as the direct shear stresses or the indirect or torsional stresses. Now, other than stress, now because of stress, the material actually experiences the change in dimensions. And the term which defines the change in dimensions is called strain. So strain is defined as the change in length upon original length. As you can see in the cylindrical bar, if the original length is L and if it is acted upon by an external load P, then del L is the change in length that part may experience. How much change in length will happen, that depends on the mechanical property. So this del L, change in length to the original length, this property is termed as strain. Now the sign convention, the tensile strains or the tensile stresses are positive. The compressive stresses and compressive strains are considered as negative. Similarly, because of normal stresses, there are normal strains. Similarly, because of shear stresses, there are shear strains. And so shear strains, it's because of the shear stresses. And is actually the shear strains are measured by the angular deformation, right? Now the relationship between stress and strain was very importantly discussed by Hooke. There's a person, very famous person, whose name is Robert Hooke, and he has developed a relationship between the stress and strain. He has given the law. This law is known as the Hooke's law, and it's set within the elastic limit. The stress is directly proportional to the strain. So if you double the strain will be doubled. If make the stress half, then the strain will also be half. So the variation of the stress and strain is actually linear in nature, and therefore the ratio of stress and strain is a constant. This constant is where constant of material, and it is very important constant. It is known as the modulus of velocity, and this modulus velocity is independent of dimensions, and naturally you can see that it is a ratio of stress and strain has no unit. Therefore the modulus velocity has the same unit as the stress. Right, this is again the when you if you have the modulus velocity, you can find the uh, change in dimensions because it is a ratio of stress to strain. Stress becomes restoring force upon resisting area. Strain is change in length upon original length. With this formula, we can find the change in length, which is P into L upon A into E. This is a very useful formula when we try to find the change in length, right? And E is assumed to be same in tension or compression because the material we are assuming is isotropic. Now, when we talk about the stress and strain, there is a very important curve that is shown here. It shows the relationship between stress and strain. And this is the variation of stress and strain for a ductile material like mild steel. And as you can see here, till the on the y-axis you have stress, and on the x-axis you have strain. And the variation of stress and strain is initially linear because it follows the Hooke's law, directly proportionality. And beyond the A, you have some, the linearity is actually disturbed a bit. And then after a point B, which is called the yield point, and C lower yield point, B is upper yield point, the material enters into the plastic stage. And as it enters into the plastic stage, one can see a lot of strain for a constant stress, or even if you reduce the load, even you can see the stress. But beyond the point C, you can suddenly see the rise in stresses, and that's happening because of the material is acquiring the strength in the plastic region. This phenomena is known as strain hardening. This continues to, the strength continues to increase till the point D, where the D is called ultimate tensile strength point. And you can see beyond the point D, the curve dips again, and the necking will start. So the material will actually, you know, makes a neck, and this neck keeps on elongating till you get a fracture point. That is the point D is called the breaking point or the fracture point. So this is what we have seen, the proportional limit, elastic limit, yield point, and the strain hardening region. After the yield point, you can see the gain in strength and ultimate strength, and finally necking and rupture. This was the behavior for a ductile material where you can see a lot of plastic deformation as well as elastic deformation. Now, if you take any brittle material like cast iron, you can see here there is deformation only in the elastic range. As soon as the material enters in the plastic stage, it gets failed. So immediately you can see after a point Y, the material is actually is failing. So the point B is failure point, and one can see elastic deformation, but one cannot see any plastic deformation. That's the behavior of the brittle material because they are considered weak in tensile loads. So they have very low plasticity, or they don't show any deformation in the plastic region, right? Now, these properties are, what we have seen is the static properties through tension test. Then there are dynamic properties. Then repeated loading, fatigue loading also happens. This is the specimen that we have used for the tension test. And you can see the LG is the gauge length where the deformation is considered. And between the, total length L, there is a free length also. And deformation and the circular cross section is considered. So you can see a circle which represents the cross section of the specimen. The other property that's of also very prime most importance is hardness. It is the resistance of the material to the penetration of another hard body which do not receive a permanent set, right? So it's actually the resistance to the plastic deformation. And that's very important because whenever we see two surfaces rubbing against each other, the harder surface tries to, create the impression on the softer surface. Like you see the tire moving on a soil or the tire moving on a road. The road is actually being harder than the tire and tries to, fear the tire material. And if the tire is moving on a, softer surface like a soil, the tire will try to make an impression on the soil. So the hardness comes into the picture. Now to measure the hardness, the popular method is the ball indentation test. That's called the Brinell hardness number or Brinell hardness test. Here you can see the ball shape indenter is there. And it is trying to create the impression. Now the Brinell hardness number is actually defined as the load that we have applied to create the impression to the whatever area of the indentation. So F is actually the area in a square millimeter square, and P is the load. When you divide this, you get the Brinell hardness number, and the area formula when we put, you get the Brinell hardness number as 2p upon pi d inside the bracket d minus under root d square minus small d square, where capital D is actually the indentation ball diameter and small d is the diameter of the indentation or the impression that we have created. Now this was the Brinell hardness number, but there are some limitations, and Brinell hardness number is depends on the load, and as this when you increase the load, you can see the geometry of the indentation changes, and for the very hard material sometimes we may not be able to get the exact values. So this is the limitation, and moreover the indentation that we create from the Brinell hardness test is usually larger in size, so that indentation is not usable anymore. To overcome this difficulty, some other hardness tests were invented. One of them is Vickers hardness test. It produces procedure is exactly same, that you apply the load and you measure the area, but the indenter is different. It is a diamond indenter, and it's actually a square base pyramid having angle 136 degree between the opposite phases. There is another test which is called Rockwell hardness test. It uses the indenter that is pressed into a flat surface. The indenter is a conical diamond of 120 degree angle, and it directly gives you the hardness number instead of doing any calculation. And the impression that the Vickers hardness and the Rockwell hardness that it creates are very small, so the specimen is usable. Also, the Vickers hardness test and Rockwell hardness test, they can be used again and again. I mean, the specimen can be used again and again, because in the Brinell hardness test, you can't, because of the higher size of the indentation, sometimes it's not usable. Well, the another property is called impact testing, that is testing, but the property that it measures is called toughness. In the impact test, a notched bar specimen arranged either as cantilever or simply supported beam is broken by a single blow in such a way that the total energy required to fracture it may determine. Now, we see around many cases where the accidents happen, road accidents happen, and this property comes into the picture, where large amount of load is actually applied to anything, and the part on which the load is applied, how much energy that part is absorbing, it's actually the measure of toughness. And uh, generally, uh, the parts which subjected to shock load or impact load, There the toughness is very important because it is actually the amount of energy that is absorbed before failure. Now the toughness is tested by two methods. One is known as the ISOT method, another known as the Charpy method. Both measure the toughness. The only thing is that, as a standard, the type of the specimen that ISOT uses is slightly different than the type of specimen that Charpy test uses. The ISOT test, the specimen is arranged in a cantilever way, and in the Charpy test, the specimen is arranged in a machine as a simply supported beam. So you can see that cantilever beam, one end is fixed, other is free, and here both end is simply supported, and the striker will strike it. You measure the energy before striking, and once the striker hits the specimen, you get the energy of the striker after the impact, and the difference of the energy before impact and after impact is actually the energy absorbed by the specimen, and that's the measure of toughness, right? So some of the problems that is one has to deal with on tension test that's given. You can see a mild test specimen. There's a diameter of 16 mm and a gauge length of 80 mm. Load is given, extension is given, and ultimate load, total extension, diameter at fracture, cross-section area as fracture is given, and the original cross-section area is given. And one is to find the modulus velocity based on the formula. Ultimate tensile strength, simply divide the ultimate point divided by the original area. Yield point divided by the area that gives you the yield strength. The percentage elongation, that's also very important. So the percentage elongation and the percentage of area, they are the measure of ductility, and they also have to be measured. So this is very elementary exercise. And another exercise is that if you have a specimen with 16 mm dia and 18 mm length, and if you are applying the load 6 kilonewton and extension was 0.034 mm, determine the proportionality stress and the modulus velocity, because the modulus velocity being the fundamental property, one is to find out. So you just simply find the stress, divide by the strain, and you can see that proportionality stress, load upon area, and Young's modulus is stress upon strain. So dividing both two values, we get the value of stress as well as strain, and finally we get the value of modulus of elasticity. Now these are the toughness test, hardness test, and tensile test. These are the important testing of materials that you encountered as a elementary properties, and these have a very large these data that is generated through this test have a very large importance in actual design. Thank you.